Hey guys, welcome back to AlgoYogi. We are doing graph series and our next problem in the list is most profitable path in a tree. This is a really interesting problem, very intuitive and then quite lengthy actually. And solution is also going to be pretty lengthy. Let's go through the description. There is an undirected tree with n nodes labeled from 0 to n minus 1. Rooted at node 0. You are given a 2D integer array edges of length n minus 1 where edges at ith basically connects a and b. It indicates there is an edge between a and b, so a connects to b, b connects to a. Now at every node I there is a gate. You are also given an array of even integers called amount, where amount I represents the price needed to open the gate at node I if amount I is negative, or the cash reward obtained on opening the gate at ith otherwise. So let's go over this game, and I'm gonna switch the view here so that we understand the game in detail. So far we have understood that we are given an undirected graph. Now where we are given edges, where these pair of values in edges connects those two nodes. Now we are also given amount array, which is basically the same size as the graph, and for each of the node there is an amount, or you can say it's this price amount that basically people receive when they open the gate. So it's part of the game. So 0, 1, 2, 3 and 4. So we are given 5 nodes. So let's put these amount on each node. So for 0th node the amount is -2. So if it is -2 and there is a player over there and they reach there, that means there is a gate, and to open the gate they will have to pay basically 2 unit of dollar or whatsoever. Let's consider it's dollars. So they'll have to pay $2. If it was positive, then they get that dollar, and if like there are 2 players that get there at the same time, then they will basically, the amount will be half if it's a gain, or and same goes if it's a loss, then they both pay equally after dividing it by 2. So now if let's just complete this. So 1 is 4, so this is positive, then 2 is 2, and then 3 is -4, again negative, and then 4 is 6. Alright, so we have labeled the price associated with each node that will cost the user or give them the gain. Now let's go through the rules of the game. Initially there are 2 players, by the way, Alice and Bob, and initially Alice is at node 0. So in all the game there will be different games, right? This is just one example. So in all the games Alice is at node 0, and Bob is at node, it's called Bob, and in this example Bob is 3. So basically Bob is right here, so at 3. So Bob in this game is right here. Now at every second Alice and Bob each move to an adjacent node. So basically Alice will move to its adjacent node, which is 1, and then from here she can either go to 2 or 3. So but it's like she can choose to go in one of those nodes in 1 second. So this is 1 second she takes from moving from one node to the adjacent node. Now Alice and Bob each move to the adjacent node. Alice moves towards some leaf node, and Bob moves towards node 0. So Bob currently is at 3, and Bob is trying to move to basically 0, where Alice is currently at. Now for every node along their path, Alice and Bob either spend money to open the gate at the node, or accept the reward, right? So these negative values is the price, and these positive value is the this is the cost they pay, and positive values are the price they get. So this is the reward. Now if gate is already open, if the gate is already open, no price will be required. No price will be required. So let's say if Alice was moving, to some leaf node like this, but then Bob was already here, and Bob must have opened this gate. That is why when, let's say, this is Alice moves to this node 1 second, and then here second, basically 1 and 2. So at time 2 she's here, but Bob was present at 3 when it was basically time 0. So that is why this negative value, Bob has already paid that, right? So that means if Alice is getting here, that means she wouldn't have to pay this price. All right. Or if it was positive value, then also she wouldn't get anything. It will be 0. All right. So now let's move forward in the game. If Alice and Bob reach the node simultaneously, they will share the prize reward, both thing, for opening the gate. In other words, if the prize is open the gate is C, then both Alice and Bob pay C by 2. Similarly, if the reward is C, then they both gain C by 2. If Alice reaches a leaf node, she stops moving. Similarly, if Bob reaches node 0, he stops moving. Note that each events are independent of each other. This is the key to solve this problem. Now we need to return the maximum net income Alice can have if she travels towards the optimal leaf node. Optimal leaf node. So what we can do right now is, since these two basically movements of Alice and Bob, they are independent of each other. However, this is the time which is common in between both of them, and that time in association with the node that they are present at that particular time, right? So that is basically we have to keep in mind. Otherwise, these two traversals can be done independently. And now if it is just about the time, how about we basically do one traversal? We can choose Bob's traversal, which is basically this. Bob needs to go to 0, and whatever path Bob takes, then we will run a DFS, and we can store for that particular node Bob travels. For any particular node Bob travels, we'll store that time in the DFS. So Bob will start with 0 time at 3, then Bob will take a step to 1 to reach 1. From here Bob can reach to 2 or 0. So let's say Bob reaches 0, so here time is, for Bob time is 0, for here time is 1, for here time is 2, and we will store for Bob in something called Bob time. We can store that into an array for each node. So 0, 1, 2, 3 and 4, we have 4 nodes, and we will be starting at the Bob node and running a DFS. So what we'll do is, we can solve this problem in 2 steps, right? Okay, let me get rid of this. What are those steps? First thing is step 1. Step 1 is run DFS on Bob's traversal to node 0 and store Bob's time into an array. So let's say we call it Bob time. All right, this will be Bob time. So this is the array that we will be creating, where Bob's time is being recorded at every second. It reaches all these different nodes while reaching 0, and whenever it reaches 0, that's when we will just return true, and then just come out of that DFS. So that is step 1. What is step 2? Step 2 would be, now run DFS on Alice's paths to different leaves and collect gains by looking at the time in Bob time, because this will help us decide if Bob has already been there. That means if it was price, he has already paid, or if it was the profit, then it's Bob has already taken. We will basically receive 0. But there might be a situation where Alice has her own time as well, right? Like she is traveling with time, right, each second. And if those time basically match with each other, that means they both reach that node at the same time. So basically this is what I'm saying. So if Bob is here, Bob moves in 1 second to 1. Alice is here, and Alice moves in 1 second to 1. And when they are both here at second 1, then this particular reward, which is 4 divided by 2, which will be 2 goes to Bob and 2 goes to Alice. So that is what will happen, but we will get that because we have already stored Bob's times for these nodes. When Bob reached at 0, 2 or 3, here the time is 0, time is 1, time is 2. I've already said that, and at time equals to 1 is where Alice also meets Bob. And then once that happen, and then finally, then you can finally return the max of all rewards Alice could collect. So I'm not gonna write the pseudocode here because it's really long, but we can just definitely dive deep into it. It's not a crazy problem, it's just like a lengthy solution. So if I write it, it's gonna be very straightforward, and we'll just in detail cover everything. All right, so as I said, first let's create the graph. We are given edges, that's something we always do. So we'll create a graph is equals to default text of type list. Then let's go over for A and B in my edges. So graph A's neighbor is B, so I'm gonna append B, and then I'll do vice versa. So for B I will add A. Alright, so our graph is ready now. Graph is ready. As I said, we're gonna run 2 DFS. It seems crazy, like in the beginning, like how would you solve this problem? It's just like a crazy number of steps. But what we're going to do, run DFS on DFS for Bob. Alright, so let's send Bob to 0th node. Alright, so let's run DFS for Bob, but before that let's create Bob time array, and initially let's just put some infinity value. Like infinity value will indicate that Bob never went to those nodes, because Bob's objective is to get to node 0. So here we can just say float infinity in Python, and then multiply it with length amount. So length amount, this gives us basically the length of our size of our graph. So let's call DFS. So we will call it DFS Bob, and what we are sending into it, we are gonna start we're gonna send the U, basically start node, source node, which is going to be Bob. My bad, I wrote 0, Bob. Then we are going to send the time, which is 0, and then we are going to send the parent node, which is -1. The reason we are sending parent node is because it's a undirected graph, and in undirected graph we want to make sure that we don't stuck in a loop for if for A's neighbor, B would be present in A's neighbor, and when I visit B's neighbor, A would be present. So it's like a loop. So here we can just provide this U, then this 0 is the time, so I'll just call it time, and then -1 is the parent. All right, so if this U is equals to 0, that means I have reached I've reached the destination for this, for Bob. But before that what I'll do is into my Bob time I will add for that U, I will add that time and then return true, because I reached there. I'm just like, there is no point of returning true or anything. I just want to return something, or you can just, for you yourself, you can just have return. But here what I want to do is now I want to explore all the neighbors of U. So for V in graph of U, this is what I was talking. So if this V is equals to parent, equals to parent, then I can continue for visiting other nodes. Otherwise, okay, so you can see the code. Nice. So otherwise what I'll do is I can check if it's possible to reach basically 0 from taking these paths. So if the DFS, this DFS running at V, so I'm sending in V as the source node now. Time would be whatever time I have, time plus 1, so second, it's like you're incrementing 1 second, and then parent would be this time U. All right, if this is the case, then again I want to basically put this time for U. For U, I will put this time, and then I will return true, because I was able to reach to basically here. Okay, and then finally I can just return false. If, let's say, if I never get there, that means I will be coming out and then I never reach 0, so I just want to return false. Okay, so I have already called this. I hope you can see. Now we have filled this. What we want to do is we want to run DFS for Alice. Right? So sorry, my bad. So DFS for Alice now, and that will be starting at 0, reaching, we don't have a destination, but time will be 0, and -1 will be the parent, and we can even return this. So that will be our answer. Now let's write this. So DFS Alice. So to DFS Alice, we have our source node U, then we have time, so let's call it T, and then we're gonna call this parent. So here there are a few things that we want to do. First is we just fill this Bob time, right? We just fill this Bob time. If the T for Alice is less than what Bob's time to reach at U, then I will have, you know, this gain variable. I can just initially have this as 0. Then what I'll do is this gain would be initially, this gain would be because I'm reaching there earlier, then I will get all the amount, whatever is plus or minus whatsoever at that position. All right, so this will be, so I think we don't have to mention it here because we will be running either of these. So this is one case. Else if this t is equals to the time that Bob took to get there, right? This is the time that Bob took to get there at that particular node u, and if Bob gets there at the same time, then gain would be basically whatever the amount at u divided by 2. Else, the last case is you get the gain would be 0, because now Bob is going there after Alice is going there after Bob. So that means either Bob has paid the entire price, or Bob has gotten all the reward. So we don't really get anything. So Alice doesn't get anything here. But let's have a variable called max. So now we'll be going to each child and also thinking if those child could be, you know, the leaf node, or those child can lead to leaf node. So initially, let's say these child node would be bringing me let's say negative infinity value, you know, negative infinity value. I'm just assigning the minimum value, but I will, so that I can calculate the maximum out of all those paths, right? And also, let's say is leaf true, because I have to get to the leaf. So initially I'm marking it true, and it will only be true if if I'm trying to access my parent. All right, so initially I will just say true. So for v in graph of u, if v is equals to parent, then I will continue. And let's say if I passed, you know, I basically got out of this for loop without, you know, going down, that means I am basically I come out. So that means I have declared this is leaf true. So my is leaf would be basically come out as true. Otherwise I will mark this false, which means not just this parent was this v's neighbor, this u's neighbor, not only this u's neighbor was v as its parent, but it had other neighbors as well. So it's not just u and v are connected. There are more nodes inside this. It's not just u and the parent connected. There are more nodes inside this graph u. So u is connected to more nodes. So that means that's not a leaf node. Leaf node will only have one incoming degree. So I will mark this false, and marking this false meaning I will have to run DFS on this child. So this Alice DFS Alice, what I'll do is max child would be maximum of either whatever this DFS brings me on v. So I'm running it on v. Time would be whatever time we had. So did I write time or t? So I think I wrote just t. So t plus 1, and then for parent I'm sending u. All right, so this will give me, either it will be max negative infinity, or there will be some value returned from here. So this value could be a few different things. First is either just gain, and this gain would be we will return gain if we were accessing just the leaf, right? If we were just accessing just the leaf, if that was not the leaf, that means we explored some other nodes along the path, and this max child must have returned something from those paths, else we can return this plus gain, whatever gain have happened at the U node, basically source node. So I guess that will be all. Let me zoom out so that we can see the entire code. That will be all. So max child plus gain if it's not a leaf node. If it is a leaf node, then you just return the gain, whatever you calculated over here for you, because there is no need to travel from the leaf node. All right. So now we are returning, DFS Alice. This will be returning me the maximum amount that Alice can collect. So as I said, like, it's a lot of code, but this is quite easy. This is really easy. This is step 1. We run DFS on for getting Bob to node 0, and at the same time we just fill in this Bob time, and once that Bob time is filled, then you run a DFS on Alice, trying to get to all those leaves, all those directions that she can take using DFS, recursively calling DFS on these child nodes for U, or again for V's neighbors, and then until Alice gets to the leaf node, that's when she'll get either the gain from if that she's standing on the leaf node, otherwise she'll get the maximum child plus gain. So let's run it. I guess you can see this entire code. Yes, it runs. Awesome. So let's write down the time and space complexity. Time complexity for this would be, so we are running 2 DFS, but they are both independent of each other, right? Aren't they? They're both independent of each other. That is why the time complexity is going to be, we can say, big of V plus E, or you can say twice of V plus E, because there are 2 DFS, and one DFS at most is going to visit each node once. And for space complexity as well, we are storing everything in our graph, so that is also going to be V plus E. So that will be all. See you guys later in the next video.